And the next talk will be another remote talk, this one from TOPLAS, on a metatheoretic reasoning for extensible languages. Go ahead and take it away.
Thank you. I'm Don Michaelson, and I'd like to tell you about our TOPLAS paper, Modular Metatheory for Extensible Languages. So in our view, extensible languages are built by combining independently developed components from an open library to make languages. And so by an open library, we mean one where components can be developed and introduced independently of other components and also of other authors. So our underlying assumption here is that combinations of components should just work. The user lists which components they want to use, and then from that list, they get a workable language specification, including the features from all the components. So prior research has shown how this is possible for both syntax and semantics based on modular checks for the components being well-formed. So here, just works means for syntax, creating an LR grammar, and for semantics, creating a full language definition. And so in our work, we extend this approach to metatheory. So the components can state properties that they expect the combined language to have. Then they can prove those properties modularly, the modular checks for our approach. And then those properties are guaranteed to hold for any combination based on those modular proofs. That's where the just works come into our approach. So before we discuss our modular metatheory framework, we need to look a little bit more at what our language extensibility framework is that we're proving properties about. So in our language extensibility framework, we have two types of modules, or two types of components. So we have the host language, which is unique in a language library and provides a base of definitions for the library that's shared by all the components. This introduces syntax categories and constructors, as well as semantic relations and rules defining them. So extensions add new features to the base definitions extending the host language. So they can add new syntax constructors, new rules, and they can also add new syntax categories and new relations, so they can meaningfully participate in defining the language. So then in a combined language, we have all the syntax and all the semantics from the included components, which is the host language plus some number of extensions. And so when we're building a language in this modular fashion, we stick to a principle of how we write the definitions. So if we're defining a particular relation or a particular construct, then that should be defined by the component that introduces the construct or the component that introduces the relation. So these are the two, and it depends on which one knows both of the pieces. And so this makes sure that the language is well defined because it's a component that knows both pieces well enough to give a good definition. But sometimes this isn't possible. So if I write an extension that introduces a relation, you write an extension that introduces a construct, neither of us can define this relation for this construct because neither of us knows both of them. So to get complete definitions, we introduce a notion of projection that we can use to complete the definition. So a projection is a translation towards the host language, getting rid of a top-level extension-introduced constructor and instead representing it in terms of some host constructors. So then we can lift our semantic definitions for this relation from the projection back to the original construct. So this gives us complete definitions so that all relations can be defined for all constructs. And so that tells us how our framework works, but why are we interested in a framework like this? So let's look at a simple example. So consider having a host language that introduces some simple expressions, as well as typing and evaluation for them. So then we can have an extension introducing list syntax, as well as typing and evaluation for that. So with the list extension, we can now use the host language syntax, as well as list expressions, instead of using linked list records. So we get a little bit easier, it's a little easier to write programs. Consider another extension introducing information security. So this gives a static analysis that determines whether an expression is public or private based on the sensitivity level of data stored in the variables that might be used in the expression. So this extension is giving us something new that wasn't in the language before. We can check that private information isn't leaked to public places in evaluation. So this is entirely new. The host language didn't have anything like this. And what's more, with this language framework, in a combined language, we have everything from all three components. So now we can use list expressions in a program while also getting this check that the private information doesn't leak. So even though they were written independently, we can use them together in languages from now on. But currently, without metatheory, information security extension isn't really giving us anything because we don't know for sure that its analysis is guaranteeing what it claims. Which brings us to proving metatheory for these extensible languages so we can get the benefits of extension introduced relations as well. So in our metatheory framework, we have two types of properties. Foundational properties, which are introduced by the host language and provide a foundation for the metatheory of the full language, similar to how the host language's definitions provide a base for the definitions of the whole language. So for example, we'd have the host language might introduce a property that its static typing ensures we don't have type errors in evaluation. Then we have auxiliary properties, which are introduced by extensions. So these are auxiliary because they're only relevant when the extension introducing them is included in a combined language. So our information security extension would introduce a property that its sensitivity analysis does guarantee there isn't any private information leakage. And so our key objective here is that we want modular proofs of these properties that are introduced by any component to ensure that they're going to hold for any combined language. And so this guarantee is going to come from creating a complete proof for any combined language based on the modular proofs. So for foundational properties, this isn't too hard because they're known by all the components being introduced by the host language. And so all the components can participate in the proof. So we can orient our proof around case analysis on a relation. Then we get cases for each rule, and each component can prove the cases for the rules that it introduces. So then to create a full proof, we can take each of these, all these cases that are relevant, put them together to get our proof. So the difficulty here is that these proofs often rely on having a complete knowledge of the language due to using case analysis. So the solution is to restrict the proofs so that they apply in any combined language in addition to the single component in which they're written. So things are more difficult for auxiliary properties. We only have one extension that knows the property, so it has to provide the full proof work by itself. But it doesn't know what the other extensions are going to introduce because they're independent of it. So our solution here is to use projections to understand the unknown extensions, similarly to how we use projections to understand unknown extensions for defining relations. This is going to rely on projection constraints. So these are foundational properties that relate the semantics of extension-introduced syntax to the semantics of its projection. So for example, we might say the free variables of an expression have to be the same as the free variables of its projection. So these properties specify how similar a term and its projection must be. So then we can use this information to write a generic proof that will apply to proving the property holds for any construct from another extension. So in this case, we know because it's from another extension, the extension introduced relations have to be defined by lifting from the projection. And we know that the projection constraints hold to relate the host language's semantics across the projection. So then the generic proof is going to assume that the property holds for the projection. And then using this information, we're going to prove that we can then lift the property back to the original construct that projected. Excuse me. So then to build a combined proof, we use this generic proof as well as proofs the extension can write directly for rules that it introduces or that the host language introduces. Then the generic proof expands into an actual proof for every case for constructs from other extensions. And then we have all the cases covered, and we have a proof of the property for a combined language. And so once again, as with foundational properties, our modular proofs have to be restricted because we only know part of the language. But overall, these restrictions, while we might expect them to be a little bit restrictive, being restrictions, Overall, the cases other than the generic proof are not too difficult to prove. They're much like proving a metatheoretic property without modularity. So the difficulties, when there are difficulties, come in the generic proof, and these arise from the effects that the projection constraints the host language chooses has on what we can prove in extensions. So consider choices between, say, stronger and weaker projection constraints that restrict the semantics extensions can introduce more or less. So contrast a projection constraint saying that evaluation results have to match exactly across projection versus one that says an expression and its projection only have to have the same free variables. In the former case, the semantics introduced by extensions have to be very similar to those that are already present in the host language. Or in the latter case, the extensions can be more different from what the host language introduces. However, it's kind of these affect how we can prove auxiliary properties, because if we know more about extensions with stronger projection constraints, it's much easier to prove auxiliary properties because they're more similar to what we already have in the host language. With weaker projection constraints, it can be more difficult, or sometimes not even possible, to prove auxiliary properties that we might want, because we don't have enough information to even know if the property will hold. It might be that the property will not hold for constructs from other extensions. So the choices that the host language makes affect what properties extensions can introduce, but while those choices do matter, what we want to make sure that you know is that projection constraints do permit us to prove properties from any extension for any combined language based on these modular proofs. And because we can do it for properties from the host language and from any extension, its properties from any component for any combined language hold based on modular proofs. And of course, we aren't the first people who thought about trying to have a modular approach to developing metatheory. Excuse me. So there's kind of two bodies of previous work, depending on the kind of language they're considering. We consider all the previous work to fall short on some of the goals that we have. So the first body of work is for languages that we call complementary components. So these share declarations of syntax categories and relations, but all the syntax constructors and all the rules are introduced in co-equal language fragments. So there's no host language here. So in this kind of framework, there are only shared properties, similar to our foundational properties. And they end up having proof restrictions similar to ours. They don't have a notion of the individual fragments introducing properties. So for languages more like ours, host language and extensions, components building on components, there are a number of works, but there's kind of three categories for the drawbacks that we see with them. So some works say the extensions aren't independently developed. So somebody, the same group of authors develop all the extensions and make sure they work together, and then you can choose a subset of them. Other works do have independent extensions, but if I write an extension and you write an extension, there's no guarantee they're going to work together. Somebody has to put them together, test them, and possibly tweak the definitions to get the proofs to work. And finally, there are some systems where extensions are basically syntactic sugar. They can be developed independently and they're guaranteed to compose, but they can't really significantly contribute to the language. They have to be basically just macros for the host language. So what makes our work unique is that we support open language libraries, meaning we have independently developed extensions, compositional guarantees, and significant extension participation altogether. So, in conclusion, in our paper, we develop a modular metatheory framework, which permits any component in the language to introduce properties. Those properties can be shared as foundational properties, or they can be unique to each component as auxiliary properties. And then we explain a way that you can prove these modularly, either through distributing it to all the components for foundational properties, or having the extension that introduces the property prove it entirely itself for auxiliary properties. The paper also includes a soundness result for our framework, showing that these modular proofs do in fact guarantee that the property is going to hold for any combined language based on being able to take these modular proofs and turn them into a complete proof. Our paper also includes a demonstration of the effectiveness of our framework with a small language proving foundational and auxiliary properties for it. And finally, our paper introduces implementations of both the language framework, which is Sterling for writing the components independently, and Extensibella for writing the modular proofs for them. In addition, Extensibella implements our soundness result, taking the modular proofs and combining them to create an Abella proof, where Abella is a proof assistant, so we're producing machine checkable proofs. And both of these implementations are available at our website. So for future work, we have kind of two threads that are really tied together by needing to exercise our framework more. We have some examples of using our framework, but to test whether it's practical, we really need to have larger examples with more properties that we try out. We also need to have more examples testing the effects of projection constraints. Within even the same language definition, there are many choices that we can have for projection constraints, ranging from very strict to very loose, strong versus weak, and also choosing which semantics to restrict and which not to restrict. So an exploration of both of these will benefit our work in determining whether it's generally applicable and when it's applicable and when it's not. So thank you. We have a link to our paper here, as well as one on the PLDI program, and I'd be happy to take questions now.
Questions for the speaker? I'll start off with one. So early on, you had this assumption that with extensions, they must compose. This kind of assumption that composability must just work. But then later, when you compare it to related work, you say other related work does not provide this composability guarantee. So how are you avoiding sort of circular reasoning and saying we assume they compose, but we also give a guarantee of composability?
So what we're assuming is that they should compose, not that they do. So we're saying in our framework, this is how it should be, and so we need to come up with restrictions and proofs that this is actually going to be the case. So we don't assume that they compose. We restrict things so that we do get the composability.
Cool, thank you. Other questions? All right, one there.
Can you give us an example that the meta theory of one extension becomes invalid because of the introduction of another extension? And in that case, how do you deal with this conflict?
I'm sorry, I think I missed part of your question. Can you repeat that?
Can you give an example that the meta theory of one extension becomes invalid because of the introduction of another extension? And how do you deal with this conflict?
Yeah, so we prevent this by restricting the proofs that we can write. So when we're writing a proof in a modular fashion, we write it in such a way that it's not going to be invalidated by definitions that are introduced by another extension. So the main way that this happens is in case analysis. So if we have case analysis on something, and in the context of a single component, we have, say, 3 rules that are applicable. Same case analysis in the context of a combined language might have 4 rules that are applicable. So our main restriction on the proofs that prevents adding new extensions from causing the proofs to be invalid in a combined language is restricting case analysis to cases where we know all the proofs, we know all the rules are already known. Other extensions can't introduce new ones. And that's based on our principle for definitions where only certain components can introduce rules. So I think that answers your question. Please do follow up if it's not clear.
All right, thank you. And with that, we are out of time. So let's thank the speaker again.